Before we continue on in section 2.7, does anybody have any homework questions?
Yes. Yeah. So like the one with pluses, like the second to last one, I think, or is it second? Like the third to last one. Oh wait, what? I'm just kidding. I was talking about the what was due last night, but yeah.
Oh, okay. Do you want me to look at that?
Also, yeah.
There was a question on that one. I think it's the second one. Yeah. That one.
Did I or did I not just enable that? Okay, this one?
Yes, ma'am.
Okay, so when you have two decimal places, to write your answer as a fraction, you put a 1 with 2 zeros underneath, like that. So this has two decimal places, so I'll put 587 over 100. This has 1, 2, 3, 4, 5 decimal places, so I'm going to have 5 zeros in my denominator.
Wait, how did you divide like that?
I use the slash, the forward slash, on the question mark key. Here I'll have one decimal place. So there's a 0.4, so one decimal place, so one 0 in my denominator. Here I'll have 1, 2, 3, 4, 5. 5 decimal places. So 5 zeros in my denominator. Negative 6 over 1, 1, 2, 3. Oops, that's not 0. 1, 2, 3, 4, 5. So hopefully I counted right on these. So count how many digits are to the right of the decimal, and that's how many zeros go in your denominator. Any other questions? So the square root of 2 is irrational. We proved that in class. However, this number is not irrational because the square root of 2 divided by the square root of 2, those divide away. So you get just a plain 3 divided by 5. So the answer is no. The quotient or product of two irrationals is not always irrational. Any other questions? So if you put this in your calculator, you'd have 3 divided by 5 or 0.6 for your answer. We are in section 2.7. We are looking more closely at the real numbers. The real numbers are all the numbers on the number line. So all the numbers that you know, unless they have an I in them, but we don't look at numbers with I when we look at the real numbers, just all the other numbers that you know. Those can be divided in a number of different ways. One way to divide them up into two sets is to make the rationals and the irrationals. So the real numbers can be divided completely into two sets, rational numbers and irrational numbers. And that's how we're looking at them this morning. Remember, the rational numbers can be written how? How can the rational numbers be written? Go ahead. Yay. As fractions, where a divided by b is your fraction, b is not 0, and a and b are integers. So irrational numbers definition is real numbers which are not rational. Well, all of the real numbers can be placed on the number line, and it's easier to do that if they're written as decimals. For example, if I tell you 392 divided by 5, it's probably going to be something that you write out as a decimal so you know where to put that on the number line. So we're going to look at decimal expansions here. For example, if you have 1/3, the decimal expansion of 1/3 is 0.3333 ... Or if you had 1 4/5, that decimal expansion would be 1.8. So we looked at irrational numbers as well. Square root of 2 we proved was irrational. You can find where it goes on the number line if you put it in your calculator. I get 1.4142135562. That does not end there though. My calculator just runs out of digits. If it ended there, I could write it as a fraction. I would put it as a fraction over 1 with 1, 2, 3, 4, 5, 6, 7, 8, 9 zeros. It does not end. I'm going to put ... but I do not know what the pattern is after that. There is no pattern. Or how about pi? Is another irrational number. So I put ... because even though my calculator runs out of digits, this does not end. If its decimal expansion ended, then I could put it over a power of 10 like we did in the homework for Wiley here. So looking at these examples, can you see the difference between the decimal expansion for rational numbers versus irrational numbers? What can we say about the decimal expansion of rational numbers? Yes?
Follows a clear pattern.
It does. It follows a clear pattern. Yep. So this 0.333, you know, goes on forever. In fact, the clear pattern is a repeating pattern. That's the decimal expansion of rational numbers. It could just end, though. This one just ends. So the decimal expansion of rational numbers terminates, or ends in a repeating pattern. The decimal expansion of rational numbers terminates or ends in a repeating pattern. The decimal expansion of irrational numbers does not terminate and does not end in a repeating pattern. The decimal expansion of irrational numbers does not terminate and does not end in a repeating pattern. So we have the definition of what the rationals and irrationals are up here. And a characteristic of that definition is how their decimal expansions play out. So I'll give you a list of some numbers and you can circle the ones that are rational. Does anybody have any questions before we do that?
Please bring it up.
Thank you. My kids think I have eyes in the back of my head, but I don't actually. So we have 0, 1.232323 dot dot dot, square root of 5, negative 2/3, 1.3123456789101112 dot dot dot. So go ahead and circle the ones that are rational. Okay, circle 0 or not? Yes. So 0 over 1. So circle 0. 1.232323 dot dot dot. Yes. Okay, so there's the repeating ending. Square root of 5? No, not rational. Okay. Can't be written as a fraction. Negative 2/3 rational? Yeah, we circle that one. How about 1?
No, because we never have a pattern.
Can you write 1 as a fraction?
Yes.
You can write 1 as a fraction, 1 over 1. The document camera decided to restart itself.
But it wasn't 1, it was like 1.1234.
No, there was a comma in between the two.
Oh, I didn't even
Yes.
see that. I was like, wait, that's not wrong. That's just going on.
Does anybody have a commercial? I have a commercial. Study group. Study group. Math 100 study group today, 1 to 2 in Wood Hall, 202. And Wednesday, 4 to 5, ES 304. So, I need longer commercials. So 1, how do you write 1 as a fraction?
1 over 1.
Yeah, 1 over 1. 3.123456789101112 dot dot dot.
Yeah.
What?
No, no,
Wait, no.
It's not?
not rational.
Oh, good. I thought you were saying it was rational. I was like,
So the ending is a pattern, but it's not a repeating pattern, so it is not rational.
Oh.
So that's kind of a trick. Okay, so watch out. Just because it's a pattern, that doesn't make it rational. It has to be a repeating pattern. And we're going to see why. Why is that? First, we'll figure out how to write how to write a rational number.
Can you bring it a little bit? Thank you.
Thank you. How do you write a rational number with a repeating pattern as a fraction? So this is a skill that I'll expect you to be able to work on Friday's quiz. How do you write a rational number with a repeating pattern as a fraction? So these other numbers in the list we wrote out as a fraction, but this number we did not. So that's what we're going to see. How do you write that 1.232323 ... How do you write that as a fraction? Now this is going to take almost a whole page. Oh no, this won't. Never mind. You're fine. Sorry. Yeah.
I had a question about the quiz.
About the quiz? Okay.
What is it that we can like bring?
Oh, on Wednesday for the practice for the quiz, can you please print out the study, the tentative, I think I took out the word tentative study guide.
Is that on Canvas?
It's on Canvas on the home page.
Okay.
So print that out and bring it to Wednesday's class, please.
And that's what we can use in all the things.
You cannot use it on the quiz, but Wednesday we're going to fill in the questions. Make sure everybody's ready for the quiz, hopefully.
Why did I have like a note card?
You can bring a note card, so you can put as much of that on your note card as you desire. For your quiz, you can bring a 3x5 note card. Here we examine this 1.232323 ... and say, how many decimal places repeat? Yes? 2. So 2, 3. So multiply by 100. Okay? From 2, we need 2 zeros. So if we'd have had 3 decimal places repeating, we'd multiply by 1,000. If we'd have had 1 decimal place repeating, we'd multiply by 10. Multiply by a power of 10 with the same number of zeros as you have repeating decimals. Now you can do that in your calculator if you want to, but don't round off. So call this number n that we're starting with. And now we're going to have 100 times n. Now you can do this by hand by moving your decimal place 2 to the right. So my decimal was between the 1 and 2. Now I'll move it 2 places to be between the 3 and 2. So because I'm multiplying by 100, that moves the decimal place 2 places to the right. And again, you could do that in your calculator, but don't round off if you do. Once you've done that, then you subtract your original number. As you subtract, you'll have to line up your decimal places. So I'm going to subtract the n, so I'm going to say minus n. And the n is equal to 1.232323. And I need the decimal place to line up. So I put the 1 decimal place, 2, 3, 2, 3, 2, 3. If you've chosen your multiplier correctly, your power of 10 correctly, when you subtract, the digits will subtract away, the repeating digits. So 3 subtracts from 3, 2 subtracts from 2, 3 from 3, and so on. So I'm left with 123 minus 1, or 122. On the left side over here, I had 100n, 100 times n, and I'm taking away 1n. This is a 1n. If you don't see a number, you can put a 1 there. So 100n minus 1n is 99n. So all of the repeating part subtracts away if you're doing your multiplying by the proper power of 10. And you don't make any errors when you do that. You can divide away the 99 now. So n will be 122 divided by 99. Sometimes you can reduce that. You don't need to worry about reducing for my class. These are easy to check. So you should get the answer in your calculator. 122 divided by 99 is 1.232323 repeating. If you're using your calculator, remember, don't round off. The whole point of this is to write the exact value as a fraction that you have as a decimal. So the key to this then is counting how many decimal places are repeating, how many digits repeat, and that's how many zeros go in your number you're multiplying by. So 100, because we had 2 decimal places repeating, so 2 zeros. This is something you should practice for the quiz Friday. You'll get a question similar to this. And it does take a little practice to remember what to do. It's easy to make up questions to practice, though. You can make up your own fractions, your own decimal, your own repeating decimals, and then check them. We'll try another one, though. Do you have any questions first? This one's a little harder, a little bigger. We have 42.019,439,439,439. What will we multiply by on this problem?
1,000.
Good, 1,000. 3 repeating numbers. The fourth, 943, 943. So use the 1,000, 3 zeros. So this is my number n that I'm starting with. And now I'm going to find 1,000 times n. So I move my decimal 3 to the right, or I put it in my calculator and multiply moving 3 to the right. Well, when I multiply in my calculator, the decimal you'll see move. So I have 42019, and then the decimal point now, instead of between the 2 and the 0, the decimal is now between the 9 and the 4. So write down the rest of what you had, 4, 3, 9, and so on. When you go to subtract, make sure you write all your digits nice and neat, all lined up properly with the decimal point, lined up with the decimal point, and then the 42 under the 19, and then 0, 1, 9. If your digits aren't in line with each other, where they're the same digits and the repeating part, then you've made an error somewhere. So that's my n. And I'm subtracting it. So the 9 subtracts the 9, the 3 the 3, the 4 the 4, and off to the right as well in the dot 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 where that keeps going on over and over again. That's getting subtracted as well because they're all lining up now. Except up to here. When I come to the 3 and the 1, here you could take out your calculator if you want. 42,019.43 minus 42.01. Or you can do it by hand. I'm going to do it by hand and then check my work.
Bless you.
So 999n equals 41,977.42. This one still has a decimal in it. So there's going to be one more step on this problem, multiplying to get this decimal out. So I have 2 decimal places. I choose to multiply by 100 on both sides of the equation. Because there's 2 decimal places, I need 2 zeros to multiply to move the decimal to the right there. So now I have 99,900n equals 4,197,742. Let's divide both sides of the equation by 99,900. Oh, I'm going to check it, but first I'll write it out. So I have the 42.019439, and then I have a 4 because the next digit would have been 439. So because there's a 9 over here, my calculator does not truncate. Instead, it rounds this to a 4.
Like, what's the point of doing all of that if we knew, like, from the beginning that that was what n was?
So this is n as a decimal. This is n as a fraction.
Oh, okay.
So your problem on your quiz will say write the number as a fraction of integers. I'm going to give you another example for you to try. Does anybody have any questions before we do that? I'm going to pick one out that I already did so I can walk around and help you if you're stuck. So the number to write is 4.12121212 dot dot dot. Did we already do that one? No, we didn't do that one. I have 3 classes and I get them mixed up sometimes. If you're stuck, raise your hand, please.
So here is this the number?
Well, I'm
Did
gonna
I
multiply.
miss the step?
Yep, yep. And then you take the 100, and then what do you do with the 100? I know. Yeah, that's why I asked you.
Okay. Is it this?
Take the 100 and
That's right. That's where it started. That was just another example, so I remembered that it's how I would do it. So. And this is second?
Oh, how did you get that number?
I think that was the number you gave us.
This one is the number.
Right, but this one,
So it gives you the 1.23.
yeah, which I put over here. 4 point.
Yeah. And then we took the 100 on this one, and we used the 100 to get this one. By multiplying. So this should say 100 and 100 and 4.
Oh.
100 and 4. Yeah, so this is 100 times that
Equals that.
Yeah, so if you take this number, multiply by 100, you get the answer.
So this would be. Is what you're saying, okay. I just had to know that that's what
Okay.
Okay.
You are well on the way.
Thank you.
What else? All the stuff's right except what did you get? 8 minus 4. You get 8. Oh, when you even lose. Then on this side, you subtracted 100 from, yeah, so this is 99. So in the end, you'll be 12 and divide by. Does anybody need help?
So we do a little bit of algebra. We take 100 times the number, and then line up the 100n minus the 1n. And when you subtract, you get 408 on this side and 99n on this side. So once you have the 99n equals the 408, then you divide out the 99 and get 408 over 99. Does anybody have any questions?
So it is 408 over 100?
It is, yes. Well, we're going to see, why does a rational number have to end up written as a repeating fraction? or terminating fraction. This is what's going to take a whole page. Why do rational numbers end in a repeating pattern or just terminate? Why do rational numbers end in a repeating pattern or just terminate? So we'll look at an example of a fraction and see through long division why this has to be the case. So we'll look at the fraction 45 divided by 7, and we'll use long division to see how come this has to become a repeating decimal or just terminate. Hopefully you remember your 7's multiples. 7 divides into 45 6 times. So we'll put a 6 here. And then 6 times 7 is 42. So we write 42 and subtract. 45 minus 42 is 3. So I need more digits. So I'm going to put a decimal place after the 45 and a decimal place after the 6 and keep going. So 45.0 and bring down the 0. 7 divides into 30 4 times. 4 times 7 is 28. And now I can subtract and get 2. And put another 0 and bring down the 0. 7 divides into 22 times. 2 times 7 is 14. I'll go ahead and subtract and get 6. Bring down another 0. 7 divides into 68 times. 8 times 7 is 56. Sixty minus 56 is 4. So I need more zeros. 7 goes into 45 times. 5 times 7 is 35. 40 minus 35 is 5. Seven divides into 57 times. 7 times 7 is 49. So I'll subtract here. 50 minus 49 is 1. I'll bring down another 0. 7 divides into 10 one time. 1 times 7 is 7. So we'll go ahead and subtract. 10 minus 7 is 3. We need another 0. 7 divides into 30 4 times. 4 times 7 is 28. And subtract and get 2. This is your Canvas activity, by the way, and we're supposed to go through 9 decimal places. So hopefully you have space for 9 decimal places. 4 times, let's see, now I have a 20. 7 goes into 20 twice. 2 times 7 is 14. And subtract and have 6. We put a 0 here. 7 goes into 68 times. 8 times 7 is 56. subtract and get a 4. I guess that's 9 digits. I could keep doing this forever though, right? But the question is, why do rational numbers end in a repeating pattern? Because you see, what numbers would be repeating here?
4, 2, 8, 5, 7, 1.
Good. 4, 2, 8, 5, 7, 1. And we started that again. 4, 2, 8, 5, 7, 1. 4, 2, 8, 5, 7, 1. But the question is, why? All rational numbers, all these fractions, if you play them out with long division, you'll see that they must start over again. We started over at the 4, let's see, because when we subtracted, we got a 3. And so then we got a 3 again. And that, as soon as we got the 3 again, then we had to start over. Why is that going to happen every time you take and do the long division that makes up a fraction? This is actually a principle we learned in chapter 2. Okay, so as you're doing your long division and you're subtracting, what are the possible numbers you could get as you're doing the subtracting when you divide by 7? What are they? You could get a 0. If you got a 0, you'd be done, right? Okay. If you get a 1 or 2 or 3 or 4 or 5 or 6. So these numbers, when I subtract, I got a 3 here, 2, 6. What would it, if I got a 7 or 8 or a 9 or 10, what would that have meant when I subtracted? I did something wrong, right? You can't, when you subtract, if you get a 7 or 8 or 9 or 10, you didn't pick a big enough number up here to multiply by. So these are the only choices when you subtract, the only outcomes. So there were only 7 possible outcomes, one of which would have meant our fraction just terminated. Whenever you're doing division, whatever this number is, that's how many possible outcomes there are in your subtraction. So how does this tell us if we divide out to 9 decimal places that we're going to be repeating when we had 7 possible outcomes? Anyone remember the name of that principle? Good. It's the pigeonhole principle. The pigeonhole principle said if we have only 7 possible outcomes and we're dividing 9 times, one of those outcomes has to be used at least twice. At least one of those outcomes has to be used twice. And that's what happens. So once you start repeating by subtracting and getting the same number, then you're starting the cycle over again. And that's the same for any rational number. So that's why all rational numbers, decimal expansions, either terminate or end in 0. So go ahead and take a picture of that and put your name there in there. We're examining the real numbers. The real numbers are dense. On Friday, we looked at two numbers and found a number in between. Even though the space between them is only 1/1000th, we found a number in between. We found I can't remember what was in each class, but I think in this class you might have said 1.4025. If you put another digit, which would have to be a 0, after our thousands place, then you're a little more easy. It's a little easier to see that the 1.4025 falls between the 1.402 and 1.403, because this ends in 20 and this ends in 25. And I could do this again. I could find a number between 1.4020, I'll say 0, because that's the same, and between 1.40250. So in between these 1.40200 and 1.40250, I could put 1.40201. And there's actually infinite numbers. This is a rational number, but there's actually infinite numbers in between any of these two numbers.
Okay, so why is that 201 instead of 225?
That's another example. Got it. So that's another example, 1.40225, that falls in between those. So there's actually, you're right, every one of us could come up with a number that's a rational number, and we could come up with an irrational number in between these. So here's an irrational number. So the number 1.402, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. That falls between this number and this number. Because this digit, instead of a 0, is a 1. So it's bigger than this number. And because it's a 1, it's smaller than this number that has a 5 there. But it's irrational. You might think that the rational numbers were more prevalent because that's what you use most often, right? You use the counting numbers most and you use the fractions most. But it turns out that irrational numbers are vastly more populous than the rational numbers. So we're going to make a number here that's irrational. Well, I presume it will be. Everybody write down a digit, please. A number between 0 and 9. Everybody write down a number between 0 and 9. And we're going to build a number. So this is, you're going to be my random number generator. I'll start us out with a whole number and then we'll go to a decimal. And I'll just snake around the room. So tell me the number you wrote down, please, the digit.
2.
2, okay.
7.
7. What did you write, KJ?
3.
3.
7.
7.
7.
7.
4.
4. 7.
Changing my thing.
4.
4. Rico? What digit did you write down?
7.
7. What one?
4.
4? No, 8? Okay. Okay.
3.
3.
1.
1.
7.
7.
8.
8. 2.
4.
4.
9.
9. 8. 6.
7.
7.
6.
6.
2.
2.
6.
6.
8.
8. Who's next?
5.
5.
8.
8. And we can keep going like this, especially if we had a random number generator, so I didn't have to have you do this all the time. What are the odds that this is going to repeat or end in zeros? Nobody picked any zeros. Okay, so if we keep doing that forever, what are the odds that that would repeat in the end, so that it was a rational number because it had a repeating end, or that it ended in 0, 0, 0, 0 because everybody picked 0, or my random number generator kept picking 0? What are the odds of that? 0. There is no chance of that happening. Irrational numbers vastly outnumber the rational numbers, which is kind of weird because that's not the kind of numbers that we're used to. It actually raises a philosophical point. We as people tend to hang out with people who have the similar ideas and start to feel like that's how people are, but that's not necessarily the case. Just because that's what's familiar doesn't mean that's what's common. And that's the case with numbers. What's familiar isn't necessarily what's common. Well, we'll have to stop here. Wednesday, please bring your review sheet and we'll go ahead and review for the quiz Friday. I'll see you then.
I actually need to talk.